this session. Today we are going to discuss the homomorphism and isomorphism of algebraic structures. Let us go for what is the definition of homomorphism and isomorphism and others. Let us consider two groups. One is G and another is G1. G is a group under the binary operation star, and G1 is a group under the binary operation star 1. So this is another binary operation. B, two groups, and F is a mapping from G to G1. Then F is called homomorphism. F is called homomorphism if for all A comma B belongs to G, F of A star B, because A, B are the elements of G. So there, whatever the binary operation will be there, that binary operation we have to consider. So A star B, F of A star B is equals to F of A and F star 1, F of B. F of A and F of B which are in G2. See, it is a G2 and this is G1. And of course here the binary operation is star 1. Here the binary operation is a star. So I'm going to select any two elements here, A and B. Then in between there is a binary operation star and their images are F of A and F of B are the images. So under these the binary operation is a star 1. So whenever this condition is satisfies, then the mapping is, then the function is, we are calling it as a homomorphism. Now, let us observe here, F is G to G1. Suppose F is from G to itself, and the above said condition, that means this condition is satisfying, then that means F is defined from G to G itself and it is a homomorphism. Then that function we are calling it as endomorphism. A function is said to be endomorphism if it is homomorphism and defined from the group G from G to itself. Next, another one is a function is said to be epimorphism. See here, G function is from G to G1. This condition is satisfied, so we can call it as a homomorphism. This is instead of G to G1, if we are taking Z and it is satisfying the homomorphism condition, then it is the endomorphism. So now this function is homomorphism and onto, then it is known as epimorphism. A function F from G to G1 is said to be epimorphism if F is homomorphism and onto. Then the another one is monomorphism. What is a monomorphism? Here also F is a function defined from G to G1 is said to be monomorphism if it is a homomorphism and 1-to-1. And next, when the function is said to be isomorphism, it is homomorphism, 1-to-1 and onto. So whenever these three conditions are satisfied, then the function is said to be isomorphism. And isomorphic relation we are going to give on like this. G is isomorphic to G1. G is isomorphic to Z1. Suppose instead of taking G, F is from G to G1, if I am taking F is from G to G, and the function is homomorphism, 1-1 and onto, then such mapping is called automorphism. So it is nothing but an isomorphic of a group G into itself is called an automorphism. So these are the different ways we are going to represent what is meant by a homomorphism, what is meant by endomorphism, what is epimorphism, what is monomorphism, what is isomorphism, and what is automorphism. Only thing is, where the function from G2 itself or the other than Z. So based on that, the names are going to be changed. And now the kernel of homomorphism. What is the kernel of a homomorphism? So it is f is from G to G1. The set of all elements G mapped onto the identity element of Z1 by the function f, then it is known as the kernel of f, or nothing but kernel of the homomorphism. That means whatever the elements, so this is Z and this is Z1. So here the set of all elements, that means f of a is equals to 1, E1. So we are considering all the elements. So here f is a group from for G2 into G1 is the set of all elements G mapped onto the identity element. So here whatever the elements that were, it is mapped to the identity element, the set of all elements of A1, the set of all elements of G, it is known as a kernel of homomorphism. So this we have to consider the kernel of homomorphism. Now we are going to discuss some of the examples. So what is a homomorphism related examples? So here this is Z is the integer, and next E is the even integers, and of course here plus and here plus, addition is the binary operation. Then we are going to define f is from Z to E, integer 2 and even integers, integer 2, even integer, f is defined like this, and we are going to define f of x is equals to 4x. We have to verify whether it is a homomorphism or not. So for that, let us consider any two elements in Z, Then what is the image of this is? Image is if it is f of x and f of y, f of x, f of y. So the binary operation is xy. So here we are taking x plus y is also a member because it is a group, it is a closed under addition. So subsequently x plus y is also a member. So f of x plus y is equals to 4 into function defined as 4x. So 4 into x plus y. So that is 4x plus 4y. So it is nothing but this is f of x and this is f of y. So f of x plus y is equals to f of x plus f of y. So whatever the function that we are defined, which is nothing but a homomorphism. Now let us consider the another one is f is a mapping from G to G dash. G to G dash is nothing but G is a real number system and G dash is nothing but a positive real number system. So the function is defined as like this. F of a is equals to 2 power a. F of a is equals to 2 power a, whether it is a homomorphism or not. So for that, two elements if I am going to consider from G, from the real number system, so that is nothing but a plus b, and so then f of a plus b is nothing but 2 power a plus b. So it is 2 power a into 2 power b. We can write it as, so this is f of a and f of b. So f of a plus b can be written as f of a into f of b. So here we can say that the first one is, see this is the addition binary operation. So R is a group under the binary operation is plus, and another G dash is R plus is, it's a group under the binary operation multiplication. So for that reason, here the multiplication will be there. In the previous one, both binary operations are addition. So we are getting this is the addition. So here, one is addition and another one is a multiplication. So the image here, it is a multiplication. So we are taking here f of a plus b, and here we are getting f of a into f of b. The image is lies in R plus, so it is a homomorphism. It is a homomorphism. Now let us consider the other example. Let R be a group of real numbers. R be a group of real numbers under addition, and R plus be a positive real numbers under multiplication. So now we have to verify whether it is a isomorphism or not. So when we say that a function is isomorphic, it should be a homomorphism, it should be a 1-1, and it should be a onto. It should be onto. Whenever these three conditions are satisfied, then the function is said to be isomorphic. So now we have to verify whether it is satisfying or not. So it is nothing but the previous problem. So whatever 2 power a instead of 2 power a, here we have e power a. So then we are going to homogeneous is nothing but the which is similar to the previous one. Now we are going to verify whether it is 1-1 or onto. So when we say that a function is 1-1, when we say that a function is a 1-1, so a function is said to be 1-1, different elements will have different images. Or whenever the images are same, f of a is equals to f of b, then their elements are also, the pre-images are also same. So now f of a, we are going to define, this is e power x. F of x is equals to e power x. So we are going to take f of a is e power a. And f of b is equals to e power b. I am just taking, or just considering their images are same. So e power a is equal to e power b, which implies, so this is possible only a is equal to b. So the images are same, subsequently the values are also same. We can say that f is 1-1. F is a 1-1. Next, we have to prove this ontoness. So here it is R and it is R plus. Now it is not possible to verify each and every value. So for that reason, we are going to take one element in R plus, and if it is having a pre-image, then we can say that it is onto. It is onto. So what is that pre-image? We are going to find out what is that pre-image. So here, f of logarithm of c. What is f of logarithm of c? F of x is e power x. So it is nothing but e power log c. So it is nothing but to the base e only. So e power log c is equals to c. So c is having a pre-image logarithm of c. Whether logarithm of c will be there in R or not. So anyhow, whatever the positive number we have to consider, for that there will be a positive integer, that is nothing but a positive real number. Logarithm is exist, so that is also a real number. So definitely log c belongs to R. So we can say that c is having a pre-image and the pre-image is a log c. So we can say that the function is onto. And of course, the homomorphism, while we are going to consider the homomorphism, so first one is, it is group under addition, and the second one, it is group under multiplication. So I am going to take a comma b are any elements in R. Subsequently, a plus b also an element in R. Why I can say that a plus b is also an element? Because it is closed under addition. So definitely a plus b is also member in R. So now f of a plus b is equals to, what is f of x is e power x. So f of a plus b is e power a plus b. So it is nothing but e power a into e power b, and e power a is nothing but f of a, and e power b is equals to f of b. So we can say that it's a homomorphism. It is a homomorphism. So the function is 1-1, onto, and homomorphism. Then we can say that it is isomorphic. Now let us go for the other example. So here, let R be a multiplicative group of positive real numbers, and here, see, this is R plus to R plus. Both are defined, the function is defined from R plus to itself. R plus to itself. Now, we are going to verify, we are going to show that it is automorphism. It is automorphism. What is, when we say that it is isomorphism? When we say that it is isomorphism, whenever the f is a mapping from G to G dash, both are not same, whatever the conditions are satisfied, that is 1, 1, onto and homomorphism, it is isomorphic. The same conditions, it is going to be satisfied, and the thing is, the function is from the group onto itself. So R plus to R plus, then we can say that it is a isomorphic, is nothing but a automorphism. Now, so let us consider any two elements. So here I am just taking R plus. See here, R is be a multiplicative group. Multiplicative groups. That means it is given as both are. R is a group under the multiplication, and another one is R plus. R plus is it is also a group under multiplication. So now here we have to consider any two elements, x comma y members in R plus. So if it is a positive real number, then their product is also a positive real number. So definitely it is also a member in that. It is also member in R plus. So now f of x comma y. So f of x into y is, so it is f of x is x square. So it is nothing but xy whole square. So it is nothing but x square into y square. F of x is x square is nothing but f of x. And similarly, this I am going to take it as f of y. So f of xy is equals to f of x into f of y. So we can say that it is a homomorphism. It is a homomorphism. Now the next one is, we have to prove that it is 1-to-1. It is a 1-to-1. So for that, we have to take the images are same. F of x is equals to f of y, which implies x square is equals to y square. Then this is, I am taking it as plus or minus x is equals to plus or minus y. So here only positive integers are there, positive real numbers are there. So I am taking x is equals to y. So subsequently x minus x is not a member here. So it is not at all a function. It's not at all a function. So I'm not going to consider the negative real numbers. So I'm just considering only the positive. So f of x is equals to f of y implies x is equals to y. So we can say that the function is 1, 1. The function is 1, 1. And next, ontoness if you are going to prove. So ontoness is, let us consider here, I am just taking x, and what is its pre-image? Pre-image is nothing but f of root x. F of root x. So what is f of root x? Is nothing but root x whole square. So it is equals to x. It is equals to x. So its pre-image is root x. Because x is a positive integer, so root x is also a positive real number. Positive real number. Suppose if it is defined as r negative, r, if I am taking r alone, I am taking as instead of r plus, if I am taking r, then definitely it is not at all onto. Definitely it is not at all onto, because there is no pre-image for negative real numbers. Negative real numbers. So here it is r plus to r plus. So definitely for all positive real numbers, there will be a pre-image. It has a pre-image. So you can say that it is onto. So function is 1, 1, onto, and homomorphism. And the function is defined from r plus to itself. R plus to itself. So isomorphic is imply isomorphism actually. But isomorphic, the function is defined from the G2 itself, or R plus to R plus. So we can say that it is automorphism. It is a automorphism. Now let us go for the some of the basic properties of homomorphism. So here, let G1 and G2 are two groups, and F is defined from G1 to G2. Be a homomorphism, it is given as homomorphism. Then E1 is the identity element in G1, and subsequently E2 is also an identity element in G2. And then F of A inverse is equals to F of A whole inverse. This is true for Augury. GA belongs to G1. And H is a subgroup of G1. H is a subgroup of G2. And H2 is also a subgroup of G2. H1 is a subgroup of G1. And H2 is also a subgroup of G2. And next, if F is a isomorphism from G1 on to G2, then F inverse is a isomorphism from G2 to G1, G2 on to G1. Now, let us go for the proof of this. So, here, F is a homomorphism. It is given now, and we are just taking, I'm just considering E2 into F of E1. See here, E2 is the identity element in G2. So then, if I'm going to multiply with any number, E1, then E2, then this will become F of E1. And so now, F of E1 is the identity element in G1. So this is E1, I'm going to write it as E1 into E1. So as to this, because I'm going to apply the homomorphism condition. So F of E1 into F of E2, F of E2. So this is E2 into F of E1, F of E1. Sorry, this is E1 only. So now apply right cancellation law. Then I'm going to say that E2 is equals to F of E1. E2 is equals to F of E1. So we are going to say that E2, and which is nothing but the identity element image is nothing but the another identity element. F of E1 is equals to E2. That means E1 is mapped to E2. So now this is the first one. And the second one is we have to prove that F of A into F of A inverse. Or else I'm just taking that F of A inverse is equals to F of A whole inverse. This we have to prove. So by using the concept of homomorphism, let us go. We are going to prove this F of A and F of A inverse, and F of A inverse into F of A is equals to the identity element. Then one is said to be the inverse of the other. Already we proved that any two elements, A, B is equals to the identity element, or B, A is equals to the identity element, then we can say that both are inverses of each other. So for the same way, we are going to take it as F of A into F of A inverse. F of A into F of A inverse. Because I am taking A is an element, any element in G1. So it implies F of A inverse is also an element in G1, because G1 is a group, every element is having its own inverse. So F of A, definitely it is a function, so F of A exists and F of A inverse is also exists. So F of A into F of A inverse, because I am going to apply the homomorphism, so this is equals to, because it is given already, it satisfies the homomorphism condition. So F of A inverse. So this is the identity element in G1, because A inverse. A is an element in G1. A inverse is an element in G1. So A inverse is also an element in G1. So which is equals to the corresponding identity element in G1 is E1. So F of E1. So what is F of E1? Already we took this as is equals to E2. So F of A into F of A inverse is equals to identity element. Now we are going to reverse this. F of A inverse into F of A. F of A inverse into F of A. Again apply the homomorphism. Then this is equals to E1. So what I'm saying that f of A into f of B is identity element, and f of B into f of A is the identity element, then f of A is the inverse of f of B. So we are going to get, this is the final result. This is the final results. This is true for all the values of A belongs to Z1. A is an element. A instead of A, if we took B, if we took C, anything, it can be the same. Now, the another one is, see, already in the last classes, we say that when a function, when we say that a subgroup, what is a subgroup of that? So here, A is an element in H1, and B is an element in H1. Then if you are going to prove AB inverse belongs to H1, then automatically H1 is a subgroup of G1. H1 is a subgroup of G1. The proof is already we solved in the previous classes. Now let us go for this. H2 is equals to f of H1 is the image of H1 under the function f, which is subset of G1. So here is nothing but just G1, then this is H1, and then it is G2, and this is H2. H2 is nothing but f of H1. F of H1 is equals to H2. F of H1 is equals to H2. So instead of proving this, so let us see here, it is given x is equals to, let us consider, we have just to prove it. Our intention is we have to prove that H2 is a subgroup of G2. So here let us, this is under this, then x is equals to f of A, y is equals to f of B for some A comma B belongs to H1. Since H1 is a subgroup of G1, H1 is a subgroup of G1, so we can say that AB whole inverse belongs to H1. Now, XY inverse belongs to, now what we are going to prove, XY inverse belongs to f of H1, which is nothing but H2, This is given already. Already we proved this. AB inverse belongs to H1, then H1 is a subgroup of G1. Now, let us go for XY inverse. XY inverse. What is X is equals to? X is an element. X is an element in, see here, we are just considering one element in that. So from the above, what we are going to say that X is equals to f of A, Y is equals to f of B. So I am just saying it as f of A and f of B whole inverse. Now this is f of A. By the above result, this is f of B inverse. So now it is f of homomorphism. If I am applying, then I am going to get this. So AB inverse belongs to f of belongs to H1. So this is belongs to f of H1. So that f of H1 we are going to take it as H2. We are going to consider it as H2. So then we are going to say that automatically x comma y belongs to H2. Then what we are going to get, x y inverse belongs to H2, and of course H2 is a subset of G2. So we can say that H2 is equals to f of H1. F of H1 is a subgroup. So this we have to prove this. See here, H1 is a subgroup of G1. H2 is a subgroup of G2. That we have to prove. For that, we are just taking x comma y belongs to H2, because here we are going to prove that H2, which is a subset of G2, and of course H1 is a subset of G1. And now if I am just taking, let us take A is mapped to X and B is mapped to Y. So now X is equals to f of A, Y is equals to f of B. Now we have to prove this x y inverse, whether it is X I am taking in X, Y I am considering in H2, we have to verify whether XY inverse is a member in that or not. So for that, XY inverse is nothing but F of A and F of B whole inverse. So which is F of A and F of B inverse. So which is equals to, by applying homomorphism, then this is. And this is already AB inverse is belongs to H1. So F of H1. So F of H1 is nothing but H2. So XY inverse is also belongs to H2. So we can say that H2 is a subgroup and which is a subset of G2. So it is automatically another subgroup. Now let us go for the other one. So here, now the another one is, the last one is, F is a isomorphism from G1 to G2. So F is 1, 1 and on 2. So now we have to prove F inverse is also isomorphism. It is given F is a isomorphism. F is a isomorphism. Now we have to prove F inverse is also isomorphism. So isomorphism, F is from G1 to G2. Let us say it is given as F is from, this is G1 and this is G2. F is from, so whenever the function is 1, 1 on 2, 1, 1 on 2 and homomorphism, then if any function is 1, 1 on 2, then it is invertible. So F inverses exist. And F is from G1 to G2, then F inverse is from G2 to Z1. So only thing is we have to verify whether it is 1, 1 on 2 or and homomorphism. So whenever the function is 1, 1 on 2, then F inverse is also 1, 1 and on 2. There is nothing to prove. Directly we can say that. And now the another one is we have to prove that it is a homomorphism. So I have to select any one value here. Let us take, I am just taking X belongs to G2 and Y belongs to G2. So XY is also belongs to G2. XY belongs to G2 because the function is defined from G2 to G1. So F inverse of XY. So it is a homomorphism. F is a, just we have to prove it is a homomorphism. For that, what is X is equals to, already it is having X is equals to F inverse, X is equals to F of A and Y is equals to F of B. And now this is F is a homomorphism. It is given already. So this will become F of AB. So now this is F inverse into F. So identity mapping of AB. So we are going to get this as AB. This as AB. So what is A is equals to F inverse of X and B is equals to F inverse of Y. F inverse of Y. So F inverse of XY is equals to F inverse of X into F inverse of Y. So we can say that F inverse is a homomorphism. Of course, F is a homomorphism concept that we are going to use here. So F inverse is homomorphism and it is 1, 1 and on 2. 1, 1 and on 2. So we can say that it is a isomorphism. F is a isomorphism from G2 to G1. G2 to Z1. Now, let us go for the other problem. Now, see here, let G be a cyclic group. Then, if G is infinite order, then G is isomorphic to Z comma plus. If G is infinite order, G is with finite order, second one, with cardinality of G is equals to n, then G is isomorphic to Zn comma plus. Z is congruence modulo n. And here it is nothing but just a integer set. Now, so here G is a cyclic group which is infinite, So now, so whenever if you are going to say that it is a cyclic group, definitely it is having a generator. So here G is having, so generator means it is G, G power 1, G power 2, G power 3, G power 4 and so on it will be. So which is nothing but generator G power K such that K belongs to G. Some integer. Now we are going to define a function from Z to Z. We are going to define a function from G to Z by, we have to take like this. F of G power K is equals to K. F of G power K is equals to K. Then we have to consider any two elements. What about the two elements which are of the form? In this form only. So for that reason, we took the elements are like this. So G power R, G power S, any two elements in G, then G power R into G power S is also a member in that, because R plus R is some integer, some value, and S is some value. Okay, whenever then automatically we can adding those two, definitely it is also a member. So G power R into G power S, just we have to verify it is a homomorphism or not. So F of G power R into S. So this is just by G power K is equals to K. So which is R plus S. So what about R is equals to G power R and S is equals to G power S. So we can say that F is homomorphism. Now we have to verify whether it is 1, 1 or on 2. 1, 1 and on 2, sorry. So for that, we are going to take the images are same. Then F of G power R is equals to F of G power S implies G power R is equals to G power. F of G power R is nothing but R. F of G power S is nothing but S by considering the function. What about R is equals to, once again, R is equals to the reverse, G power R, S is equals to G power S. So the images are same. If I am taking, the elements are also same. So we can say that it is a 1, 1. Now, ontoness, if you are going to prove, the ontoness, if you are for proving the ontoness, so any element if you are going to select here, then if it is having a pre-image, that means if I am just integer, let us say that if I am taking 4, then its pre-image is G power 4. If I am taking 5, its pre-image is G power 5. And if I am taking the K, then its pre-image is G power K. So then automatically we can say that it is onto. So the function is 1, 1, next 1, 1 onto and homomorphism. So we can say that it is isomorphic. So G is isomorphic to Z. And we are going to represent this is like this. Now the second one, this is the first one, and the second one is if G is a finite order, let us say G is a finite cyclic group, so of order n. So we are going to take it as a G power 2, G power 3 and so on. Of order n means it is like this. So this is, we are going to take it as Z. And of course, we know that how the generators will be measured and how many generators it will have, and all we are going to discuss in the earlier classes. Now, so here G is a mapping from G to Zn. G to Zn. So this is defined by like this. So here G is G1, G power 1, G power 2 and so on, it will be there. And here it is Zn is congruent to 0, 1, 2 and so on. N minus 1 will be there. N minus 1 will be there. So whatever the image if I am going to take, whatever the elements if I am going to consider, then the images are this one we are going to get either 0 or 1 or anything like that. So we are going to consider it as, we are going to take it as f of g power k is equals to k. Equivalence class. So this is a function is g, f is a function defined from g to zn, and which is defined as like this, Once again, we have to verify the homomorphism and 1 and ontoness. Then, so we can say that f is G is isomorphic to Zn. G is isomorphic to Zn. So for that, considering any two elements, all the elements are which are of this form. So we are taking G power R, comma G power S. G power R, comma G power S. We are taking the elements in G. And now, so G power R by using the function, by using this. So f of G power R into G power S. So this I am going to take it as f of G power R plus S, and which is nothing but R plus S. R plus S. So which I am going to write it as R equivalence class of R and S. Of R and S. So it is nothing but this is the homomorphism. Now the one-oneness we are going to prove. The one-oneness is we are taking the images are same. Images are same, f of G power R. So equivalence class of R is equal to equivalence class of N. So R is congruent to S modulo N. S modulo N. So R minus S is nothing but R minus S is divisible by N, or R minus S is a multiple of N. Multiple of N. So we are going to write multiple of N is nothing but G power R minus S is equals to E. So which is equals to G power R. Just that this I am going to write like this. And now this I am going to take it as G power R is equals to G power S. Subsequently images and same. Then the elements are also same. So it is nothing but 1, 1. Then the ontoness we are going to prove in the same way. That means whatever the value that we are going to assume, the k, it is having the pre-image which is of the form G power k, which is in the form G power k. So we can say that this is a ontoness, which is a ontoness. So we can say that G is isomorphic to Zn. G is isomorphic to Z. So these are the problems, some of the problems in homomorphism and isomorphism of the groups. So with this, I'm going to conclude this, and tomorrow we are going to discuss other topic. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.